Hi, I am Dr. Shyam Sarkar. Welcome to my class. In this lecture, I will discuss 20 question answer on CFSE calculation. Okay, it is exclusively for IIT-JAM because here I have shown with proper calculation and all details starting from 2008 to 2020 for IIT-JAM previous year question. So here I will first show the CFSE calculation for octahedral and tetrahedral complexes briefly, and then I will directly go to the previous year solve for IIT-JAM from 2008 to 2020 latest questions and discussion, and finally I will conclude this session with sample question answer discussion for upcoming competitive exam like CSIR-NET, GATE, IIT-JAM, SET, etc. Okay. Before going to the question answer discussion session, I suggest all of you to watch my previous video on crystal field theory part 1. Here you can get all about CFSE calculation, formula of CFSE calculation, and many more things. Okay, so you can watch this video, and then so in the second video you can get idea about Jahn-Teller distortion, dynamic and static Jahn-Teller distortion, and 15 MCQ question are there, so it will be helpful for any of the aspirants. For your convenience, I have shown here splitting of d orbitals in an octahedral field and tetrahedral field. Okay, so d orbital splits in an octahedral field into two levels, T2G level of lower energy and EG level of higher energy, and energy separation between these two levels is denoted by delta O. Whereas on the other hand, in tetrahedral field, d orbital splits into two levels. One is E level and another is T2 level, and separation or energy separation between these two levels is denoted by delta T, T for tetrahedral. Okay, and if you compare energies separation of both two fields, so delta O is always greater than delta T. And one more thing you should remember here, if delta O is less than P, then the complex is high spin in nature, and if delta O is greater than P, then the complex will be in low spin state. Okay, so if you remember these all three things, so it will be easier to solve upcoming questions. Okay, so next I will show you the formula which we will be using for CFSE calculation. So what are these in these two field? So for tetrahedral field, if any metal ions is having electronic configuration E to the power A, T2 to the power B, where A and B are the number of electrons in E level and T2 level respectively, then the CFSE for tetrahedral will be equal to A into minus 0.6 delta T plus B into 0.4 delta T. So this is the formula we will be using for calculation of CFSE in case of tetrahedral field. And if you see for octahedral field, if any metal ion is having electronic configuration like T2G to the power A and EG to the power B, here also A and B are the number of electrons in T2G and EG level respectively. So CFSE for octahedral field will be equal to A into minus 0.4 delta O plus B into 0.6 delta O plus C into P, where C is the number of additional electron paired. So you will always consider number of additional pairing energy with compared to that of spherical field. So with respect to spherical field, how many more additional pairing we are getting in case of octahedral. So that only we should consider in the calculation of CFSE. I will show you how to do that. Now here I have shared electronic configuration of first series transition metal and their corresponding metal ions, because from this portion you have to calculate CFSE. So if you do not know the electronic configuration of transition metal ions, you will not be able to calculate CFSE. So that's why I shared with you, so you can save this for CFSE calculation. See, I have shared here CFSE for octahedral complexes having electronic configuration D1 to D10 along with high spin and low spin state wherever applicable. So here I have shown you spin state and their corresponding electronic configuration, how many electrons are there in T2G and how many in EG levels, and next column is number of unpaired electrons. So how many number of unpaired electrons are there in corresponding D1 to D10 state and their corresponding spin only magnetic moment value. From this portion also question comes, and finally CFSE for all these configuration including pairing energy. Okay, so this will help you in exam because this table is the only table. From this table you will get all the answers of question asked in the examination. Okay, now I will go to the previous year solved for IIT-JAM starting from 2020 to 2008 reverse order. Okay, so let's see the first question. First question, the transition metal complexes with zero magnetic moment, zero dipole moment and CFSE of minus 2.4 delta O is or are. Since this is MSQ type question, so there may be multiple answer from these four options. Okay, so for this answer you need to first know the structure of metal ions and their corresponding structure of the complex and their corresponding metal ions. Okay, so if you make this chart like this, so it will be easier for you. See here, complexes A to D I have shown and corresponding metal ions. See, for example, for first complex corresponding metal ions is Mn minus, and for B Ni2 plus, for C cobalt 3 plus, and for fourth option, that is iron 2 plus. If you write now the number of d electrons from these metal ions, see the next column. So Mn minus d6, Ni2 plus d8, cobalt 3 plus d6 and iron 2 plus d6, and their corresponding electronic configuration if you see T2G6 Eg0, and for nickel T2G6 Eg2, cobalt 3 plus T2G6 Eg0 and Fe2 plus T2G6 Eg0. And if you calculate magnetic moment from this electronic configuration, you will get 0 for first, 2.8 for second one, and 0 for third one, and again 0 for fourth complexes. Okay, now if you see dipole moment of these four complexes, so first one is positive and rest are 0 because for other cases all are trans complexes, so dipole moment will be 0. And if you see CFSE, if you calculate CFSE using this formula I have shown below, so you will get value like this. Now if you match with our options given, see it will match with the last two complexes because here magnetic moment is 0 for both cases, dipole moment 0 for both cases, and the value of CFSE is minus 2.4 delta O in last two complexes. So it matches with complex C and D. So right answer will be C and D. Okay, that is trans COCN4H2O whole 2 minus and trans FeCN6Cl2 4 minus. So these two are the right answer. Next question, let us see. The observed magnetic moment of octahedral Mn3 plus, Fe3 plus and CO3 plus complexes are given 4.95, 6.06 and 0.0 Bohr magnetron respectively. The correct options for the electronic configuration of these three ions are respectively. Okay, so you have to find out the correct electronic configuration of these three given ions from their corresponding magnetic moment value. Okay, so how to do this? Let us see. So if you make this chart, it will be easier for you. So first write down metal ions, okay, with their corresponding number of d electrons, and then calculate magnetic moment which are given, that is 4.95, 6.06, 0.00. So no need to calculate magnetic moments, it's already given. then you have to back calculate the number of unpaired electron from this, because here you need to know how many number of unpaired electrons are there, and from this you can say which type of complex it will be. That means it will be whether high spin or low spin. So if you show this high spin and low spin, then only you can write down the correct electronic configuration of corresponding metal ions. So if you see metal for Mn3+, since it is high spin complex, it is evident from the corresponding number of unpaired electrons and magnetic moment value. So electronic configuration will be T2G3 Eg1. And for iron 3+, since it is high spin, and it will be T2G3 Eg2. And for cobalt 3+, this is low spin complex, it is evident from their magnetic moment value and as well as number of unpaired electron value. So it will be T2G6 Eg0. So if you match these three electronic configuration, it is matching with the option C. So option C will be the correct answer here. Okay. So next question, the magnitude of crystal field stabilization energy of octahedral titanium H2O6 3+ complex is 7680 centimeter inverse. The wavelength at the maximum absorption of this complex is dash nanometer. So you have to calculate this problem, and you have to round it up to nearest integers. Okay, so let's see how can you calculate this. So see, titanium 3+ is given, that means D1 electronic configuration, and T2G1 Eg0 will be the correct electronic configuration. And if you calculate CFSE is 1 into minus 0.4 delta O plus 0 into 0.6 delta O, that means minus 0.4 delta O, and absolute value of CFSE is 0.4 delta O. We will not consider negative sign here, and the given value of CFSE is 7680 centimeter inverse. Now if you compare these two, that means 0.4 delta O and 7680, so you can write down from, we know also that delta O equal to 1 by lambda. So if you put this relation, so you will get easily lambda from this. So lambda will be equal to 0.4 by 7680 centimeter. Now if you convert centimeter to nanometer, so you will get lambda max equal to 520 nanometer. Okay, so this is the required value of this lambda max. Let's see next problem. The correct order of delta O of the octahedral crystal field splitting of d orbitals values for the following anionic metal complexes is. So 4 options are given, so you have to arrange according to their delta O value. Okay, so let us see how can you solve this. So we know that 3D, from 3D to 4D to 5D. See, in my first lecture I have shown this in details, the factors affecting the delta O value you can get from there in detail. So here we know that 3D to 4D to 5D delta O increases. Now if you arrange all these 4 complexes in this chart, see complex COI63 minus, RHI63 minus, RHCN63 minus, IRCN63 minus. So corresponding metal ion, cobalt 3+ for first one, rhodium 3+ for second one, and again rhodium 3+ for third one, iridium 3+ for fourth one, and their corresponding number of d electrons 3d6, 4d6, 4d6, 5d6. Now if you see electronic configuration, that is T2G4 Eg2 high spin for first complex, T2G4 Eg2 high spin for second complex, T2G6 Eg0 low spin for third complex, because in this case cyanide ligand is there, Cn- is a strong spin ligand, so it will be low spin complex. Again for the fourth case also low spin, because Cn- is there, this is strong field. So electronic configuration is T2G6 Eg0. Now we know that, see, from electronic configuration 3d6, 4d6, 4d6, 5d6. So delta O value increases from 3d to 4d to 5d. Hence energy will be increasing from COI6 to IRCN6 3- in this order. So this matches with the option B. So option B is the correct answer here. Okay. Next question, see, Jahn-Teller distortion is observed in an octahedral complexes with d electronic configuration of. See, there are 4 options given. So if you arrange the electronic configuration of these 4, and if you see electronic distribution one by one, so for D5 high spin, so see here T2G is symmetrical and EG also symmetrical, so no Jahn-Teller distortion will be observed in this case. If you see the next option, that is D5 low spin, so here you can see T2G unsymmetrical but EG symmetrical, so there will be weak Jahn-Teller distortion in this case. So third case, D6 high spin. D6 high spin means here also T2G unsymmetrical, EG symmetrical. So weak Jahn-Teller distortion will be observed in this complex or D6 high spin. Okay. Now D6 low spin. D6 low spin means T2G symmetrical, EG symmetrical. So no Jahn-Teller distortion will be observed in this case. So see, Jahn-Teller distortion we are getting for option B and C, that is D5 low spin and D6 high spin. So the correct answer will be option B and option C, because this is MSQ type question. So multiple answer you can get. Okay. So next question, see the crystal field stabilization energy in MnH2O6 2+ is. So 4 options are given. So this is very simple question, because Mn2+, you know, Mn2+ means D5 configuration. Since water is ligand, so this will be weak field ligand, that means high spin complex. High spin complex means if you put electrons on this electronic arrangement, so you will see T2G3 and Eg2 electronic configuration. Since T2G3 Eg2, so CFSE will be equal to minus 0.4 into 3 into minus 0.4 plus 2 into 0.6 plus 0, because no pairing occurred here. So CFSE is equal to 0 delta O. Okay. So 0 delta O means option A is the correct answer here. Okay. So let's see the next question. The true statement about copper H2O6 is. So 4 options are given. So this also can be answered from the Jahn-Teller distortion. Okay, because copper H2O6 2+, that means copper 2+ is D9 electronic configuration, and D9 means T2G6 Eg3. You can see structure of this complex here. Okay, now see from this electronic configuration you can say that T2G is symmetrical and EG unsymmetrical. So strong Jahn-Teller distortion observed, and it will be Z out type elongation. So if you see my second lecture regarding crystal field theory, you will get details of Z out and Z in. So here we can say that Z out means elongation along the Z axis. So axial bonds will be longer compared to equatorial bonds. So it matches with option D, that means 4 CuO bond lengths are shorter compared to remaining 2. So D is the correct answer here. So next question, see the first row transition metal complexes having tetrahedral geometry are high spin due to. 4 options are given. So this is in case of tetrahedral field, and I have shown the splitting up in the tetrahedral field. So d orbital splits into tetrahedral field in E level and T2 level, and energy separation is delta T, which is always less than pairing energy. That's why for tetrahedral complexes we always get high spin complexes. So delta T always less than P, that means it matches with option B. So option B is the correct answer here. Okay. So next question, given that the expected spin-only magnetic moment for this complex ET4N whole 2 NiCl4 is 2.83 mu b. Okay, the total number of unpaired electron in this complex is. So you have to calculate total number of unpaired electrons. So this is very simple, because we know for nickel 2+, the electronic configuration is D8, and that is T2G6 Eg2. Now we know the spin only magnetic moment formula, mu s equal to root over of n into n plus 2, where n is the number of unpaired electron. So in these cases, you know, if you put the value 2.83 given, that is mu s is given, so 2.83 will be equal to the root over of n into n plus 2. So if you calculate from this relation, n will be equal to 2. So answer is 2. So number of unpaired electron in these complexes is 2. Also we already know that number of unpaired electron in case of nickel 2+ is 2. So answer, final answer will be 2. So next question, given that the crystal field stabilization energy for cobalt H2O62 plus is 7360 centimeter inverse, the calculated value of delta O in kilojoule mole inverse is. So you have to calculate delta O value in kilojoule per mole. Let us see how can you calculate. So cobalt 2 plus means D7 electronic configuration, that is T2G6 Eg2, and here you can see that water is weak field ligand, so complex will be high spin in nature. So if you see the splitting of d orbital with compared with that of spherical, so D7 means electronic arrangement you can see here, and so if now you want to calculate CFSE, so you have to consider how many additional pairing occurred in this case. So if you see no additional pairing compared to that of spherical field, so here pairing energy we will not consider, okay, because there is no additional pairing. So you have to remember this. So now you can calculate CFSE. So CFSE equal to 5 into 0.4 delta O plus 2 into 0.6 delta O plus 0 P, because no additional pairing occurred here. So CFSE becomes equal to minus 0.8 delta O, and see that they have supplied the value of CFSE is 7360 centimeter inverse. So minus 0.8 delta O will be equal to the 7360 centimeter inverse. So if you do not consider the sign, if you take absolute value of CFSE, so 0.8 delta O will be equal to the 7360 centimeter inverse. Now if you put the value of delta O, so delta O will be equal to the 9200 centimeter inverse. Now if you use this relation, that is 1000 centimeter inverse is equivalent to almost 12 kilojoule per mole. So you can remember this relation, because it will help to solve any other problem where this type of conversion is given. So 1000 centimeter inverse is equivalent to 12 kilojoule mole inverse. So if you put this relation into 9200 centimeter inverse, so you will get the delta O value will be 110.4 kilojoule per mole. Okay, so this is the required value of delta O which asked in the question. So final answer is 110.4 kilojoule per mole. Okay. See next question, using crystal field theory for the CONH3 3 plus ion. Number 1, draw the d orbital splitting with levels and show their electronic occupancy. And number 2, calculate the CFSE, ignore pairing energy and spin only magnetic moment value, and atomic number of cobalt is given 27. Okay, so for this complex we know that cobalt is in +3 oxidation state, so D6 electronic configuration, that means T2G6 is 0. Since ammonia is there, so it will be low spin complex, because ammonia is strong field ligand in case of cobalt 3. So for low spin complex, if you see the splitting, so if you put now number of arrangement of electrons, that means T2G6 means, so all electron will be in the T2G orbital as a paired up condition. Now if you see with respect to spherical, how many additional pairing occurred here? So there are 2 additional pairing compared with that of spherical field here. Now if you calculate CFSE, so CFSE is minus 2.4 delta O plus 2p. Okay, so if you consider pairing energy, then this is the real answer, that is minus 2.4 delta O plus 2p. But in question they have just said ignore pairing energy. Now if you ignore pairing energy, then so you will get CFSE is minus 2.4 delta O only. Okay, so no need to consider pairing energy here. So for the final calculation, now we know that spin only magnetic moment mu s equal to root over of n into n plus 2 bm. So if you put the number of unpaired electron, that is n value here, see there are no unpaired electron in this configuration, so mu s will be equal to 0. So 0 is the spin only magnetic moment. So in this way you have to answer this type of question. See the next question. Here they asked, show the levels of splitting of d orbitals in an octahedral field and calculate CFSE of high spin d6 and low spin d6 metal ions in an octahedral field. So let us see how can we solve this question. So here with respect to spherical, in case of high spin D6, see T2G and EG will be filled by T2G 4 and EG 2 for high spin, and in case of low spin T2G 6 EG 0. As you can see the electronic arrangement in both the cases. Okay, now we will calculate CFSE. So CFSE for high spin, that means it will be 4 into 0 minus 0.4 delta O plus 2 into 0.6 delta O plus 0 P, because with respect to spherical field no additional pairing occurred, so there will be no pairing energy. So CFSE in high spin state will be minus 0.4 delta O. On the other hand, in case of low spin, see all electrons are paired up in T2G level, and with respect to spherical field, two additional pairing occurred here. So we no need to consider all the three pairing, only you need to consider with respect to spherical field how many additional pairing occurred here. So if you compare with spherical field, so additional two pairing occurred, so you will consider only 2 pairing energy 2p. So CFSE is equal to 6 into not 6 into 0 minus 0.4 delta O plus 0 into 0.6 delta O plus 2p, that means minus 2.4 delta O plus 2p. So for high spin state only minus 0.4 delta O, and for low spin state CFSE is minus 2.4 plus 2p. So additional pairing occurred here. So you need to consider pairing energy for low spin state in this case. So this is how you can calculate CFSE for high spin D6 and low spin D6 metal ions in an octahedral field. Okay. See the next question. Which one of the following configuration will show Jahn-Teller distortion in an octahedral field? 4 options are given. Option A, high spin D8, option B, high spin D4, option C, high spin D5, and option D, low spin D6. Okay, so if you see the electronic arrangement of these 4 options one by one, see in case of first one D8 high spin, T2G and EG both are symmetrically filled, so no Jahn-Teller distortion. And second option D4 high spin, here T2G symmetrical, EG unsymmetrically filled, so it will show strong Jahn-Teller distortion. And in case of third option, that is D5 high spin, T2G symmetrical and EG also symmetrically filled, so there will be no Jahn-Teller distortion. And in case of final four option D6 high spin, here also both T2G and EG are symmetrically filled, so no Jahn-Teller distortion. So as you can see from these 4 options, in case of option B, that is D4 high spin, strong Jahn-Teller distortion is observed, so option B is the correct answer here. That means high spin D4 will show strong Jahn-Teller distortion. Okay. See the next question. The magnetic moment of MnH2O6 NO3 is 6.0 mu b. Find the number of unpaired electrons and show crystal field splitting and calculate CFSE. So here Mn is in +2 oxidation state, that means Mn2 plus in D5 electronic configuration. So D5 means, see here as water as ligand, so water we know that weak field ligand, so complex will be high spins in the high spin state. High spin state means electronic configuration will be T2G3 and EG2. So if you see electronic arrangement here, T2G3 and EG2, so CFSE will be equal to 0, because CFSE is 3 into minus 0.4 delta O plus 2 into 0.6 delta O and plus 0p. So no pairing occurred here, and here CFSE becomes 0 delta O. So 0 delta O is the correct value of CFSE, and number of unpaired electron is 5. Okay, because all electrons are in the unpaired condition. T2G3 and EG2 total 5 number of unpaired electrons. So answer will be 5. Okay, let's see next question. The tetrahedral complexes which always exhibit high spin state and the maximum CFSE is. See, we know that for tetrahedral complexes, either D2 electronic configuration or D7 electronic configuration will show the maximum CFSE. So you can calculate in both ways, either for D2 or D7. So it will be same. So here I have shown for D2 case, and if you see the electronic arrangement for D2 in tetrahedral field, so E electronic configuration will be as E2 and T2G, not G, T20. So E2 and T20. So this is the electronic configuration in this case, and if you calculate CFSE in tetrahedral field, so it is like 2 into 6 dq plus 0 into 4 dq. So in terms of dq, CFSE will be minus 12 dq. So it's matching with option B. So option B is the right answer here, minus 12 dq. Okay. Now I will discuss few sample questions for upcoming IIT-JAM, CSIR-NET, GATE, SET, etc. Okay, so let us see what are the sample question. Number 1, what will be the crystal field stabilization energy for COCl6 4 minus? So 4 options are given here. See, COCl6 4 minus, that means cobalt is in +2 oxidation state and D7 electronic configuration. So you can write down here T2G5 Eg2, because Cl minus is weak field ligand and the complex will be high spin. So high spin means T2G5 Eg2. So if you now put electronic distribution in this way, so T2G5 and Eg2. Now calculate CFSE. CFSE equal to, see, 5 into minus 0.4 delta O plus 2 into 0.6 delta O plus 0p, because no additional pairing occurred here with respect to spherical field. So that's why we will not consider pairing energy here. So finally CFSE becomes minus 0.8 delta O. So it matches with option C. So option C is the correct answer. Okay. Next question, what will be the crystal field stabilization energy of COCN6 3 minus? See, COCN6 3 minus, here cobalt is in +3 oxidation state, D6 electronic configuration, and it will be T2G6 Eg0, because in this case Cn minus is strong field ligand and the complex will be low spin in nature. That's why T2G6 Eg0, that means all electron will be paired up. So if you see the electronic distribution in T2G level and Eg level, so T2G6 all electron paired up. Now if you want to calculate CFSE value, so CFSE means it will be, see, 2 additional pairing with respect to spherical field. 2 additional pairing occurred, that means you have to consider 2p with respect to spherical field. So CFSE becomes 6 into minus 0.4 delta O plus 0 into 0.6 delta O plus 2p, that means minus 2.4 delta O plus 2p. So this is the correct answer. So option A is the correct answer. Okay. So next question, the crystal field stabilization energy CFSE of FeCN6 3 minus is. So let us see. So Fe3 plus means D5. D5 means T2G5 Eg0, as Cn minus is there, strong field ligand. So weak low spin complex, strong field means low spin complex, that means all electron will be in the T2G level. So if you see the electronic configuration, that is T2G5. So see, CFSE will be 5 into minus 0.4 delta O plus 0 into 0.6 delta O plus 2p. See, with respect to spherical field, 2 additional pairing occurred here. So that's why we will count 2p, and the CFSE becomes minus 2.0 delta O plus 2p. So this is the correct answer, and it matches with option B. So option B is the correct answer here. Okay. Next question, calculate the crystal field stabilization energy CFSE of CrH2O6 2 plus. See, chromium 2 plus, that means D4 electronic configuration, T2G3 Eg1, because water is weak field ligand and high spin complexes. So let us see the electronic distribution. So T2G3 Eg1, that means CFSE becomes, CFSE is 3 into minus 0.4 delta O plus 1 into 0.6 delta O plus 0p, because no pairing occurred here. So CFSE becomes minus 0.6 delta O. That means if you convert in dq scale, so 1 delta O equal to 10 dq. So minus 0.6 delta O equal to minus 6 dq. So minus 6 dq means option C is the correct answer here. Okay. So this next question, see, predict whether it is a high spin or low spin and the number of unpaired electrons present in MnH2 whole 6 2 plus. So 4 options are given. As you can see that here Mn is in +2 oxidation state, that means d5 electronic configuration, T2G3 and Eg2, because water is weak field ligand and this will be high spin complex, and the number of unpaired electron, you can see the electronic distribution in T2G and Eg level, T2G3 and Eg2, so number of unpaired electron will be 5. So high spin and number of unpaired electron 5, which matches with the option D. So option D is the correct answer here. So that means high spin and 5. Okay. Thank you so much for watching this video. If you like this video, please press the like button and you can share among your friends. Subscribe this channel to get more updates.